Hi, in this video we're going to be looking at comparing two groups, whether that's in terms of performance or scores or data, using parametric and non-parametric tests. So what I mean by that is we're going to look at the independent and the dependent samples t-tests, which are used to compare means between two groups, and it could be, for example, if it's an independent samples t-test, you can have two completely independent groups where they might both have taken or both be measured in the same way, but the cases in each group are separate. And the dependent samples t-test, which would mean that the cases were, or perhaps the participants were identical in each group, such as the case maybe in a pre-test, post-test design. And then we're going to look at also the non-parametric ranked tests, which are usable, the Mann-Whitney U-test and the Wilcox-Sign rank test, which are non-parametric alternatives of the independent and dependent samples t-tests. So we're going to do that again with the IRIS data, and we'll basically be using just two functions to compute those tests, but we'll also look at effect sizes. So we'll start by just conducting the tests themselves, looking at differences between parametric and non-parametric alternatives and how that code works. So I'll title this comparing two groups, and we'll get started. So the two functions that we're going to use are the t-test function, which is here, and you can see it in the stats package, and also the Wilcox test function from the stats package as well. So I'm going to go into the stats package and take a look at both of these. Now they both work in very, very similar ways. T-test is used for parametric tests, Wilcox tests for non-parametric. And what I'm going to do is I'm going to in this video, I'm not going to look at the assumptions testing. So you would want to check prior to choosing a test to use whether, for example, your data violates or doesn't violate the assumption of normality of residuals. And you can look to a previous video on testing normality of data on how to do that, but there's also a more extensive kind of tutorial on my website on doing it specifically in this situation, so the specific testing of that assumption for the residuals of data. But if we go to the stats package, which is in the system library set, you can see it here. The stats package has the t-test, and you can take a look at it. And these are the arguments. So this works for if you're doing a independent samples t-test, a dependent samples t-test, a one sample t-test. It's the same function, and what it asks for is for you to specify x, a non-empty numeric vector, y is a non-empty numeric vector as well, and so you can have two numeric vectors, the alternative hypothesis, a true value of the mean if you're performing a single sample test, the paired function, whether it's going to be independent or dependent, whether the variances are equal, so that's something that you would have to check if there's equality of variances, and I've previously created a video on how to do that. Confidence level, the formula, so you can see the function, so left hand side tilde right hand side, Left-hand side is a numeric variable given the data values, and right-hand side is either 1 for a one sample or paired given the corresponding groups. So I'll show you how that looks. The data that you're using and a subset. And again, as with all of these, you can get more detail as you scroll down. And at the bottom you can see some examples of how to use it. And particularly here's a very simple one. But of course this is only for 2 groups, and we've previously created data sets to do that. For example, over here you can see the Setosa versicolor data. 100 observations, 5 variables, and when you click into it, our grouping variable of species has Setosa and versicolor. So that's the format that you want your data to be in. You want to have one grouping variable. So let's see if there is a difference in sepal length between the Setosa and versicolor species. So the first thing we'll do is we'll pretend we've tested our assumptions, and we're going to use the parametric t-test. So we're going to use the t-test function. And the first thing is we can attach it first. I won't attach it. So our first thing we're going to do is we can follow this. So the numeric variable is going to be sepal length, and we want to compare that across the 2 different species. So following this kind of format here down in the description of the function. Our data is going to equal the Setosa versicolor or virginica data, because that has 2 groups. Now I can compute this as it is. It's not perfect, but we can compute it, and it will take the default values in each of these cases. So if we run this, we do get an outcome. It's a 2-sample t-test. However, there's a lot more that we really need to specify in this example. So first of all, what's our alternative hypothesis? Is it 2-sided? Did we come to this with a directional or a non-directional hypothesis? So the non-directional hypothesis, the null would be that there is no difference between in sepal length between these 2 species, and the alternative would be that there is a difference. We don't have a hypothesis about what that direction that difference would be in, and in what so what species might have either the larger or the smaller sepal length on average. That would be a non-directional hypothesis, in which case we should specify, and I will do that here. So our alternative equals, and you can see what it requests. 2-sided is the default. 2-sided. So let's run this. So that should have been a comma. So if we run this, you'll see it's actually the same. So we ended up with the same everything, because the 2-sided one was the default. But had we had a directional hypothesis, we'd be using greater or less, as you can see down here. So if I type greater, just to show you the difference, here we can see our confidence intervals are different. And if we just read the alternative hypothesis, so true difference in means is not equal to 0. So that's their non-directional hypothesis. It doesn't equal 0. The alternative hypothesis, the true difference in means is greater than 0. In other words, and you can see here, mean in group Setosa is 5.006, the mean in group versicolor 5.936, and our p-value equals 1. Whereas if I had used less, we're going to have a statistically significant result. Confidence interval, you see the other one of its infinite to negative 0.78. That's the confidence interval for the t statistic. And again, now you can see the alternative hypothesis, true difference is less than 0. So we have different hypotheses that has implications for the p-value that's outputted. So I'll clear all of that. I'm going to keep with a two-sided test for now, but that's the alternative. Paired then. So put in a comma again. Paired is going to be either true or false. P-A-I-R-D. Paired equals, let's say, true, just to show you now the difference between this. So paired data is actually not the case for this. So our data is independent. Our two species are completely separate. So it would be false. False is the correct way because our data comes from two completely independent groups. So this is for your independent samples t-test. If I run that, you'll see it's the Welch's 2-sample t-test. If I had used true for paired instead of false, it's now a paired test. And we can see that it's slightly different. We have different p-values, different degrees of freedom, slightly different t-values. Everything is slightly different. It's a slightly different test, and you use it depending on whether you have an independent samples or a dependent samples test. You can use the paired function. So I'll keep that now as false. Variance equal. So variance equal, you would have tested prior to this whether you do or don't have equal variances. So var equal, and here you also put in true or false. If our data, if we had, for example, used Levene's test of equal variances and we had found that the variances were not significantly different, we would write true. So if we were to write true, it's a 2-sample test, and if we were to write false, if we take a look at the difference now, it's a 2-sample t-test versus the Welch's 2-sample t-test, and slightly different. Look at the degrees of freedom here. They're ever so slightly different. In each case, where the means are never changing, what's changing is the exact test which is being conducted. And it's important to fully use the right amount of code, and also to have justification for what you're using. Confidence level, so it will be the last one that I'm going to put in. So we can keep this at the 95% confidence level. I will do typing into the console by mistake. You can see the way to write the code using the details on the bottom right hand pane, and we had been using 0.95 this whole time. You can see 95% confidence interval. What if we wanted to work at the 99% level though? And here you can just see our confidence intervals, that's what's changed. So 99% is here rather than the standard 95%. So that's essentially how to compute the t-test. Now what would happen if this were non-parametric, if our data violated assumptions of normality in the residuals? Well, it actually works identically, except now, because we're working with non-parametric, we're using ranked tests instead, we're going to use a Wilcox test. And again, it works the same way. So we can put in our data, and I'll just clear this. if we were to run this code, here we can see the Wilcoxon rank sum test with continuity correction. We get our W statistic and our p-value. It's identical. We literally use the exact same code, and you can find out that by looking through the package, scrolling down to the Wilcox test function, and you will see it has all of the same information that you might want. For example, that we want to include alternative, so that alternative hypotheses. And I won't demonstrate again the difference, but if we had a two-sided hypothesis, our data is paired, variance equal, we can say true or false. I'll just stick with false. And here we can see we've got confidence level and confidence interval. So this is slightly different. Conf level equals 0.95. I'll run it like this for the moment. So we get our same thing as before. What happens if we change things? For example, maybe our data was actually, it was a dependent one. Well, it was dependent cases. Still, Wilcoxon ranked test if the data being true or not. Variance equal can be set to true or false. And what you should notice is the different values. And when the data was paired, so when paired was equal to true, it was a Wilcox test. When it's false, even though it says Wilcox test, it's actually the Mann-Whitney-U test that's being conducted. But we can see the implications of doing these different tests. We can see how the code is run, and it's quite straightforward. They're identical for either the parametric or non-parametric alternatives. Now we have a separate part to this, and that's because these have just computed whether there was a significant difference or not between the two groups. And just to reiterate that, to choose on which one you would test assumptions of, for example, normality of residuals prior to this. However, and you could of course have any data set that has two different species levels. Perhaps we want to compute an effect size like Cohen's D or Hedges G or Glass's delta in the non-parametric set. So if I clear this for a moment and go back to this parametric t-test, we'll take our confidence level as before. We'll make the assumption that our variances are equal, and here's our test. And what you'll notice is we get a t-statistic, our degrees of freedom, our p-value, confidence interval for the 95% confidence interval, and our means for both groups. But what we don't get is our effect size. And to get our effect size, we want to use the Cohen's D. Cohen's D command or function from the psych package. But there's going to be a problem with this. Now it actually works in the exact same way. So first of all, I'm just going to go into the psych package just to show you. And by the same way, I mean you're giving it the same information. So if I go into the psych package and go to Cohen's D, you can see the information that you have to include. Sorry, it's not the psych package. It's Cohen's D, same function, but from the effect size package. So if I go up here and go to library, F size, so this is where we want to get our Cohen's D function from. You can see it's masked from the psych package. And I'll just go back because this is the one that we can change the different things, and you can see it here. It has the same kind of, it requires a formula to know if it's paired data or not, whether to pool standard deviations, etc. So we're going to use Cohen's D from here rather than from the psych package, and you should now see when you're typing it, Cohen's D is masked from the psych package to the effect size package. But watch what happens. If I simply take this line, we're going to get an error. So if I run this, we're getting an error because the factor has multiple levels using only the two actually present in data. Okay, so actually this may be working. But sometimes what happens is that the metadata, maybe it's not going to be, it's not going to be an implication here, but it would be might be an implication in the non-parametric one. I can't remember which one the implication comes in. But the problem that we have is the Setosa and versicolor data set that we created earlier has kept some of the metadata, so it still remembers that third level, in this case Virginica. So what we want to do is create a data set, and we want to remove the metadata of Virginica completely. So what I'm going to do is I suppose just to prove that, I can tell you the levels that are within this. So if I take this data set and I just check the levels that exist within the species variable within it, you can see that it's still got these 3 levels. So that we're getting this warning because of that, and what we want to do is have one that only has the 2 levels, and I'm going to use piping for this. So I'm going to keep it the same name, Setosa versicolor data, but I'll call it 2 for having 2 levels, and I'm going to use piping again, because what I want to do is I want to mutate it, and I'm going to mutate. I like to have a space in here. I'm going to mutate it such that the species is a factor with 2 levels. So take the species, take the species variable, and then I want it to equal a factor which has species, and you can see now as I've typed that, you can see levels has appeared. So within that, so it's going to be levels equals, I will bring that over, and specifically I just want 2. So levels equals, so and C is for a column, and the levels that I want in this one are Setosa and versicolor. And that will hopefully create for us another data set. I went slightly wrong. So I want to name that. That's what I want its name to be. And I want to take that data set and then mutate it. And now we will find up in our environment Setosa versicolor 2, just like before, 100 observations from 5 levels. But this time, when I use levels, and I'll bring this back over here, clear all of that. So if I check the levels of the Setosa versicolor data, the species variable within that, you can see I've got 3 levels. What I've done now is, with the second one, only provided with two different levels. So I'll work with that data set. Before, actually if I just take the Cohen's D back here, I'll print it again and go to 2. So if I use the first one, I'm going to get my warning message that there are more than 2 levels, but it is only going to use the 2. You can see here our warning message, factor has multiple levels using only the 2 actually present in the data. If I run this one, I don't get that warning message. Now, it has run correctly even though the warning existed, but it's better to have your code not have those warnings. So I'm going to stick with this one here using this data set. I do have some things that I can change. I can change, for example, pooled or not. We'll come back to that in a minute. But you might pooled and hedges correction are 2 of the bigger ones. So I'll say for now pooled equals true, and I'll explain what that means in a few minutes, because I just wanted here to be able to adjust it. So actually if I just do pooled equals true and run that, you can see it's Cohen's D. If I had done false, so we're not going to use a pooled standard deviation. It gives us Glass's delta. So Glass's delta is a slightly different different effect size, and that's because it's using the standard deviation only of the control group. I can change pooled back to true for our traditional Cohen's D, and if you go to my website you will find the formula for these there, or you can look up yourselves the formula for Cohen's D, Hedges G and Glass's delta. So we'll go back to the regular Cohen's D, and I'll use Hedges correction, and you can again see it's Hedges.correction. So Hedges correction equals true, and if I run this, I'm going to get Hedges G. You can see Hedges G, different effect size again, and what Hedges G does, whether or not you want to include Hedges correction, I'm trying to remember the difference. It's the correction. It's the correction for when sample sizes are small, and there's various suggestions within the literature as to when what sample size you should or shouldn't use Hedges G with. You can have them both true, so here's Hedges G with the Glass's delta correction. If I go back to pooled if I Hedges G with Glass's delta correction, it's still going to present Hedges G, but you can see the two different effect sizes and different confidence levels. They both say large. You should disregard the large there because that's coming from Cohen's recommendations for small, medium and large effect sizes, but those aren't transferable to every situation. So you should look at the effect size and interpret that relative to your own project. Other features that you have, so you have confidence level. You can see these are all presenting the 95% confidence intervals. If we go to confidence level 0.99 instead, we'll see this change. You can see it's the 99% confidence interval of upper and lower rather than 95%, and there's within. So compute effect size using within subject variation. So taking into consideration correlation between pre and post samples. True or false again is what you would put in. And then there are subjects and if you have a single sample effect size, and what to do to remove NAs in your data. So there are, it works very similar to the t-test function. The last one then, the last one to look at is the Wilcox effect size, and that comes from the ORstatics package. So I believe that's already loaded from up here. So it will be Wilcox effect size from ORstatics, and again it's very similar, but there is a confidence interval and a bootstrapping aspect to this. So I'll scroll down to ORstatics and I'll just show you the feature and how it works. I think this is here. It's not in the system library. So Wilcox effect size. You have usage, so data, formula, comparisons, paired, alternative, confidence interval, and so on, and number for bootstrap. So I'll show you really what we're looking here is the bootstrap piece. So if we go and we kind of, you can scroll down to see how it's used. We have our formula as before, so we'll take our formula and we'll take our data. We can compute a Wilcox effect size now, and it has been computed. Actually, I'll run that again. I'll just clear everything first. So sepal length between the two groups, Setosa and versicolor, our effect size, the ends, and ignore the magnitude again because we don't know if it's large really in this context. But let's take a look at what we can include. So paired data or not. So going back to whether this was a dependent or independent sample t-test. Now actually our data is not paired, but just to use true, just to show you, you can see the effect size is slightly different because it's calculating different things. So false. False is the default. Next one, our alternative hypothesis, just like before. Alternative hypothesis. Ours is two-sided. Or it could be greater than or less than, but let's take a look at the difference. So if it's two-sided, still the same effect size, but if it's greater, still the same effect size, because effect size is not impacted by the direction of our hypothesis in this circumstance. Confidence interval now. Do we want to present a confidence interval? So let's say we do. This is an interesting piece. First of all, confidence interval, and we'll say true, because the default is false. This is the only difference between, this is the big difference, sorry, not the only difference, the big difference between using the Wilcox effect size and Cohen's d. It's going to take a few minutes while it's running. You can see there's no jobs currently running. Here it goes, it's just finished. Confidence, the upper and lower confidence intervals between them. Confidence level. Let's take the 95% confidence level. Run this again. It is going to take a couple of moments. Here we go. It's slightly different. It's still the 95% one. If I change it, it is slightly different, and that's one of the things I want to come to with this nboot number of replications used for bootstrapping. You can see it is slightly different, but the default is 95, so there's no new information that's presented there. If I go to 99 instead, So what it's doing is it's taking a much, with our data it's not going to be, our data isn't really good enough to show the difference. Maybe if I go with 90. It's basically giving you an increased, so it's either the 95% confidence level, 99%, or 95%, and they're the kind of standard ones. You will see that they're all coming slightly different, and that slight difference is not because of the number that I've chosen. So if I go back to 95, I'm going to run this 3 times. So it has already run it, but it has to recompute it again every time because of the bootstrapping used to identify the confidence interval. So same code, I'll run it again. We can see now, the previous one actually when I used 95 was 0.65 to 82, now it's 0.66 to 82. The next one 0.65 to 82, and it'll always be slightly different. We can use a number in boot for number of bootstraps, so let's do 10, and I'll just show you the difference between 10 and, well, I'll see how long it takes to do it 10 times first. Very quick. You can see there 0.65 to 0.78 this time. If it was 10 versus 100, this is going to take a bit longer because it's going to simulate the data 100 times in order to give us our confidence level. Slightly longer. If I went to 1,000, so it's going to do another magnitude increase, so it's taking slightly longer again. And these are it's running longer because of the number of bootstraps, but you will see that there are different numbers coming out. I'm going to go back to 10 because 10 was very quick. So I'll just show you the need to set a seed for this for reproducibility. Run it with 10, and I can run that multiple times. Look at our differences, 0.62 to 79, 0.69 to 79, 0.67 to 82. Because it's such a low number, we're getting less kind of precision around our effect size. But you can see it changes every time. If before I run the test, I use set seed, and just do 1, 2, 3, this kind of governs our random number generator for this. And now this is what I run. I'm not going to get different responses anymore. It's all going to be the same, 0.69 to 0.8. That's really important when you're doing bootstrapping or any form of simulation to get your effect size. Also, a good recommendation would be a minimum of 500 in your number of replications to use in bootstrapping for publication. This is going to take a bit of time because it's 500 rather than 10, so it's doing it that much more. And this then would be your confidence intervals if you were to use 500 with a set seed of 1, 2, 3. But that's ultimately it. You have a parametric and non-parametric comparison of two groups. You do have to check your assumptions first, normality of residuals, and then depending on your effect size, whether the variance is equal or not, which matters for the parametric effect size, Cohen's d, Hedges g, classes delta. Setting the seed for reproducibility and number of bootstraps, number used for bootstrapping in the non-parametric variation, and to include confidence levels in when you're doing so. And I think that's it. In the next video we'll look at outliers, and we'll progress into looking at 3 or more groups, but I would recommend for a full and more comprehensive overview of doing this, including to see the formulae and the checking of assumptions, to look at the tutorial up on my website.